Chapter 1 Physical Sound. Section 1 Sound Waves. What are sound waves? Sound waves are air molecules vibrating under the influence of an initial shock, a string being plucked, a drum head being hit. Any movie with loud explosions in outer space should have the technical staff flogged in public. There are no air molecules in space. No air means no sound. The movement of the string displaces the air molecules around it. These air molecules form alternating zones of higher and lower pressure. When we say that sound is propagating, we mean that those zones are propagating. The air molecules themselves do not move in the direction of the sound. If a sensitive membrane, like a microphone, is put in front of the sound source, it will feel those alternating zones of higher and lower pressure as alternating moments of higher and lower pressure. How do we represent them? The best way to represent this type of behavior is with an oscillating function, going from some lower boundary measuring troughs in pressure to some higher boundary measuring peaks in pressure, with at some point in the middle values which represent the average pressure felt by the measuring device. Figure 1 displays a vibrating string on the left, a measuring device in the middle, and a pressure versus time graph on the right. The string creates mobile alternating high and lower pressure areas, which can be best represented by a sine wave-like function of pressure versus time. In a simple one-dimensional case, the sound pressure wave P as a function of its location x and the time t takes the form of a sine function in equation 1. P of x and t is a times the sine of 2 times pi times, open parentheses, x over lambda minus nu times t, close parentheses, where a is a wave's amplitude, describing how large or small it can be. Nu is the frequency, lambda is the wave's wavelength of equation 2. 2 times pi times x over lambda is sometimes represented by the symbol phi and is called the wave's phase. P represents the pressure recorded at a certain time t by the microphone, which is located at the x position. What is a wavelength? The wavelength lambda represents the distance between 2 points of the function which have the same characteristics, for example 2 peaks or 2 troughs. The frequency nu can be obtained with the following formula, which is valid in air, which is a linear medium, but not in water, which is a dispersive medium. Nu equals c over lambda, where c is the speed of sound. Sound travels at roughly 113 feet per second, or 343 meters per second, at 20 degrees Celsius, or 68 degrees Fahrenheit. A linear medium, like air, is a medium in which the waves with different frequencies all travel at the same speed. In a dispersive medium, like water, the waves with different frequencies travel at different speeds. The sound gets progressively deformed as it moves. What are frequencies? Frequencies are measured in hertz and wavelength in meters. 1 meter corresponds to 340 hertz, while 1 foot corresponds to 1000 hertz or 1 kilohertz. The lowest frequency a human ear can hear is called the human hearing threshold, more on that in Chapter 4, Section 4. Its value is 20 Hz and is represented by a wave of length 17 meters, while the highest frequency a human ear can hear is 20 kHz, a wave of 17 millimeter length. Standard tuning with the A note at 440 Hz is 0.78 meters long, while the wave corresponding to the middle C on a piano is 1.31 meters long. Again, note that air molecules do not travel with sound. They literally oscillate in place in the direction of the sound, which is why sound waves are longitudinal waves and why there is wind coming with them. What does move in the direction of the sound are pressure changes caused by those vibrating air molecules. Section 2. Sound volume. Sound volume is always measured with respect to some reference level and almost never in absolute terms like most other quantities are. Thus, what we think of as sound volume is in fact a ratio in sound pressure. The unit measuring sound pressure is the bell. Because we want to be able to pick out small pressure ratio differences, we do not use the bell, but the decibel, symbol dB. 1 decibel is 0.1 bell. What is the decibel scale? Since the dB is a relative scale, we need a reference point. The softest sound a human can hear is defined as 0 dB SPL, equivalent to air pressure of 20 micropascal, where 1 micropascal is 10 to the minus 6 pascal, where SPL stands for standard pressure level. Because sound pressure ratios span over a very large range of values, the dB scale is logarithmic. This means that the space between 1 and 10 is the same as the space between 10 and 100. This allows displaying much larger scales in a convenient manner. The choice of a logarithmic scale also has a physiological reason. The ear itself has logarithmic sensitivity. The equation linking the sound wave amplitude ratio R with the pressure ratio I in dB is defined as I equals 10 times the logarithm in base 10 of R squared, which in turn is equal to 20 times the logarithm in base 10 of R. How does that work? Well, imagine the pressure ratio R of 100,000. Since 100,000 is 10 to the 5, the log function yields 5, and the decibel value will be 20 times 5, which is 100 dB. For example, if the pressure at some location is 100,000 times larger than that at some other location, we will say that there is a 100 decibel difference in pressure. If the pressure is twice as high, there is a 6 decibel difference. Conversely, if the pressure difference is half, we will say there is a negative 6 decibel difference. The logarithmic scale transforms multiplication and division into addition and subtraction. Section 3. Phase and polarity. Phase and polarity are usually confused with each other, but they are not the same. The phase is the initial value of the wave when t equals 0. It is related to the time axis of the wave. Polarity, on the other hand, is related to the displacement axis of the sine wave x and represents the sign of the sine wave. Figure 2 displays a graph of pressure versus time, with phi representing the pressure at the initial time. If the pressure at that initial time is 0, then it is said that the sign representing the pressure has positive polarity. What does switching polarity mean? You will hear people talking correctly about switching the polarity of an audio signal. It means changing the sign of the signal. Some people incorrectly say switching the phase of the signal. They mean switching the polarity. But their mistake is almost logical. For sine waves, switching the polarity is equivalent to changing the phase by 180 degrees, since two sine waves out of phase by 180 degrees will cancel out. Note that two signals can be in phase but of opposite polarity and of course perfectly cancel each other out. That is in fact the only way to cancel two signals. What does checking the phase mean? In audio terminology, checking for phase coherence, or checking the phase, means making sure that all waveforms stemming from recorded instruments roughly have peaks, or nulls, at the same time so that sound does not cancel out. This is used after recording an instrument to make sure that the signals do not cancel each other. This typically could happen when recording drums with multiple microphones. If the recorded sounds are of opposite polarity, some of their frequencies could cancel each other out, making the sound thinner. This can be very difficult to pull off, especially with multiple sound sources. The best result is achieved by listening to the different sources, switching polarity of each source in turn, and selecting the result with the best sound. Section 4. Harmonics. What is a harmonic? When an instrument is played or a note sang, different frequencies are generated. The fundamental frequency, or fundamental note, and overtones, also called harmonics. The basic reason why this happens is because a vibrating string attached at both ends has very precise ways of vibrating to accommodate the physical constraints of the system, the string material, how the ends are fixed, and the medium in which it vibrates. These different waves are modes, which possess unique points with zero vibration on the string called nodes. The number of these nodes tells you what harmonic we are talking about. What is an octave? Octaves happen every time the number of nodes is a power of 2. 1, because 2 to the 0 is 1. 2, 4, 8, 16, etc. Alternatively, it can be defined as the difference in frequency between a bass frequency and its double. A semitone, or half step, is defined as 1/12 of an octave. Note that the first overtone is the second harmonic. It is only a matter of definition. They do represent the same frequency. Harmonics in between those perfect intervals become increasingly complex. Figure 3 displays two walls with an attached string in between. The first order harmonic, node number n equals 0, has 0 nodes. The second order harmonic, n equals 1, has 1 node in the middle of the string. Next, even order harmonic nodes are marked with markers of decreasing size up to 4th order harmonics. The doubling of their frequency for each subsequent octave becomes obvious. Section 5. Frequencies and instruments. In the following figure, the major music instruments, including vocal cords, are displayed with their main frequency ranges and some commonly used terminology. The first line, notes, indicates the name of the note as referenced from a standard piano keyboard with 88 notes. C1 is the first C note all the way to the left of the keyboard. C4 is the middle C. The second line displays the corresponding frequencies in hertz. Each frequency range, called type in the figure, displayed on the fifth line, has both negative, third line, and positive, fourth line, connotations, depending on context and taste. Descriptions are what they are. Understand what you can. The last line displays the full spectrum of human hearing, called standard audible range from 20 Hz to 20 kHz. You can test your limits on the internet. My upper limit is 14 kHz, which is somewhat low. I'm getting old. Dark gray covers the instrument's main frequencies, while light gray is for overtones. Instrument names are displayed approximately in the middle of their frequency range. 240 Hz for male vocals, 450 Hz for female vocals. The standard tuning note is standard A at 440 Hz, which corresponds to the middle of the range for pianos and female vocals. Coincidence? Note that trained ears can hear a difference in pitch, or frequency, of a note of 1-2 cents. A cent is 1% of the difference between two adjacent semitones. If you hear someone saying, "she's off by a couple of cents," they mean that the singer's note is off pitch by 2% in the frequency range of that semitone. If she is singing a standard A at 440 Hz, 2% is 8.8 Hz. If she is singing a high A at 880 Hz, she's 17.6 Hz off. You can test your own sensitivity on the internet. I am 90% for 5 cents at 440 Hz, which is decent. Many of the instruments on the chart have their middle range below 1 kHz. However, much of the magic in making music happens way beyond that frequency. Try to use a low-pass filter, see Chapter 2, Section 6, with a cutoff frequency of 1 kHz, and you will see why.